Hi, in this video we are going to talk about spanning trees, focusing on minimal spanning trees. So let's get started. A spanning tree of an undirected graph is a subgraph that includes all the vertices of G-graph. In general, a tree may have several spanning trees, of course, and we can assign a weight to each edge. A minimum spanning tree is a spanning tree with weight less than or equal to the weight of every other spanning tree. It has lots of applications in big data analysis, clustering algorithms, or finding minimum cost of a telecommunications company laying cable to a neighborhood, or for example protocols on the web, the spanning tree protocol. So it's very important. There are standard algorithms for solving this problem, the so-called Prince-Yarnik or classical algorithms. Both of them are greedy. So let's start with classical algorithm. First, we have to sort the edges according to their edge weights. It can be done in ordo n log n time complexity, where n denotes the number of items you want to sort. Of course, here the n is equal to the number of edges because we want to sort the edges. So we can use merge sort or quicksort. Java uses merge sort in order to sort reference type objects and use quicksort to sort primitives. So we are going to use merge sort. And it's very important to use the union find data structure or the disjoint set because after sorting the edges, we just iterate through these edges and we start adding edges to the minimum spanning tree, and we want to make sure there will be no cycles in the spanning tree. It can be done in logarithmic time complexity with the help of union find data structure. We are going to implement it and it will be clear. We could use a heap instead. It's very important in order to sort in the edges in the beginning, but the running time would be the same. So sometimes classical algorithm is implemented with priority queues. Okay. The worst case running time is ordo e log e, so we can use it for huge graphs too. If the edges are sorted, the algorithm will be quasi-linear. It's very important. Sometimes this is the case, and in these situations, classical algorithm is the best. If we multiply the weights with a constant or add the constant to the edge weights, the result will be the same. In physics, an invariant is a property of the system that remains unchanged under some transformations. So in classical algorithm, edge weights are invariant under the transformation of these weights for addition or multiplication. So let's see how classical algorithm works in practice. We don't need a starting vertex, as we will have to define a starting vertex in the Prince-Yarnik algorithm. We just sort the edges, and the smallest is the 2, so we add it to the minimum spanning tree, and we check whether there's a cycle or not. There is no cycle, so we add it. The next smallest is 3. We have to check whether it forms a cycle, and it doesn't. So we add 4. It also doesn't form a cycle, so we try to add 5, but we are going to detect that it would form a cycle, so we skip this edge and we go to 6. And 6 doesn't form a cycle, so it is the part of the minimum spanning trees. And as we have visited all vertices, it means that we are done. The total cost is 15 units. Okay, so Prince-Yarnik algorithm. In classical implementation, we build the spanning tree separately, adding the smallest edge to the spanning tree if there is no cycle. In Prim's algorithm solo, we build the spanning tree from a given vertex, adding the smallest edge to the minimal spanning tree. There are 2 implementations, lazy and eager. We are going to implement both of them. Lazy implementation, add the new neighbor edges to the heap without deleting its content. It's very important that we don't have to update the content of the heap, and that's why it is a lazy implementation, and it works in practice very fine. The equal implementation, we keep updating the heap if the distance from a vertex to the MST has changed. We are going to talk about it later during implementation. It will be clear, I'm sure. This average running time is ordo e log e, but we need additional memory space because of the merge sort with ordo e. The worst case, of course, is ordo e log v, where v denotes the number of vertices. So let's see how Prim's algorithm works in practice. We have to have a starting vertex, it will be 1. We are going to visit the neighbors, and we put these edges into a heap, and we get the min, which is 2. We visit the neighbors of the vertex 2, and we put its edges into the heap, so it's 3. And we put 3, and so in the heap we have 3, 5, and 6. We get the minimum, so it's 3, and we add it to the minimum spanning tree. Then we visit the neighbors of the 4. There's an edge with weight 4. We add it to the heap, and we get the min, which is 4. And we keep on. It's 6. We are going to remove the vertices. It will be clear during implementation, and that's why we skipped the edge with the weight 5. So it is a lazy implementation of Prim's ionic algorithm. It's very important to know what to use, Prim's versus Kruskal. Prim's algorithm is significantly faster in the limit when you've got a really dense graph with many more edges than vertices. Kruskal performs better in typical situations, for example sparse graphs, because it uses simple data structures. Kruskal can have better performance if the edges can be sorted in linear time or are already sorted. And Prim's better if the number of edges, the vertices, is very, very high. And I want to talk about what's the difference between abstract data structures and concrete data structures. For example, in Java, if you want to define an abstract data structure, you are going to create an interface. Such an interface, abstract data structures such as list, for example, it is an interface, and you are going to define the methods you want to implement in the data structures. So for example, it's a list, and array list is going to implement the interface called list, and it's going to implement its methods uniquely. And linked list implements this interface too, and it's going to implement its methods uniquely too. So it's very, very important to know that what's the difference between abstract data structures and data structures. For example, in this situation, I mean as far as Prim's algorithm is concerned, the abstract data structure is a heap. An abstract data structure is a priority queue. And this priority queue is going to use a heap, as we are going to implement the priority queue as a heap. We could use unsorted arrays, for example, but we are going to use heaps, the classic binary heaps, and I think it was very, very important. So in the next video we are going to implement Kruskal algorithm. Thanks for watching.